We're going to start with what will be a big feature on the exam, nomenclature. All right, we covered nomenclature as a good portion of every single one of those chapters that we covered in this past unit. So that's going to be a good starting place for our review lesson here. All right, and so how this is going to work is I'm going to give you guys a head start to go through and try to do these on your own. For some of the easier ones at the beginning here, I'll sort of just quietly fill in the answers, and then the more difficult ones, the ones towards the end, we'll stop and we'll go over those together. All right, and if you finish that up, you can also go ahead and count how many chiral centers we have in each one of these molecules as well, right? That's another thing that I could ask you. All right, so just to review these real quick, our straight chain alkane, you just count the number of carbons. In this case, we have 1, 2, 3, 4, 5, so that gets that prefix pentane. All right, now we got a substituent on here, so again, we're going to find our parent chain, 1, 2, 3, 4, 5, 6. All right, we're going to number our parent chain. We can do so in both directions. And in this case, we would pick that red numbering scheme because it puts that methyl group on the lowest possible number. All right, for this one, remember that your parent chain has to be the longest continuous set of carbons. It doesn't matter how it's drawn on the page, you got to find that longest continuous set of carbons. So in this case, these in blue here, these 6 would be my parent chain. And this 2 carbon group right here, the ethyl group, would be my substituent. So this would be 3-ethyl hexane. Now I got 2 substituents on there, and this is so messy it's going to drive me nuts. I'm going to rewrite it. Okay, again, I'm going to pick a numbering scheme that puts my substituents on the lowest possible numbers. If I'd gone the other direction, it would have been a 4 and a 5 versus a 3 and a 4, so I want the red. When I'm building these into my name, I'm going to arrange my substituents in alphabetical order. So methyl will come before propyl. All right, so for this one here, I'm going to find my parent chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons. If I number in the one direction, I get a 1, 2, 3, 4, 5, 6. I get a 3 and a 6. If I number in my other direction, I get a 3 and a 6. So I have a tie. And what do I use to break that tie? Alphabetical order, right? So only when you have a tie do you resort to alphabetical order to break that tie. So in this case, I'm going to pick the blue numbering scheme because ethyl comes before methyl alphabetically. So my name here would be 3-ethyl, 6-methyl octane. All right, and then for this last one here, 1, 2, 3, 4, 5, 6, 7, 8, 9. My parent chain is a nonane. 2, 3, 4, 5, 6, 7, 8, 9. Go the other way. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and which numbering scheme am I going to pick? Red or blue? Let's take a vote. Who thinks we should pick blue? Who thinks we should pick red? Okay, it's actually the red numbering scheme because I do not have a tie. If I'm going to list my locants of all my groups in the red numbering scheme, it would be 4, 4, and 6 because I have 2 methyl groups on there. If I were to list my blue numbering scheme, it would be 4, 6, and 6. So I don't have to resort to alphabetical order in this one. I don't have a tie. All right, so it is indeed the red numbering scheme that we're going to pick. When I put my name together, I'm still going to put it in alphabetical order. And importantly, I got to ignore the di, tri, tetra, all that jazz when I'm putting it in alphabetical order. So my name would be 6-ethyl 4,4-dimethyl nonane. Okay. And this would be a completely fair set of nomenclature problems to give you on an exam. A mixture of some of the easy ones as well as some of the trickier ones. In general, a nomenclature problem is around 3 points. All right, so you can get a sense of how well you would have scored on if our exam was today kind of deal. All right, the last thing I was saying is we could also figure out if we have any chiral centers in our molecules here. 3-methylhexane, do I have any chiral centers? I got one. This one right here does indeed have 4 distinct bonds associated with it. What about my 3-ethylhexane? No, right? This carbon here would be kind of the only option, and it's got an ethyl group on both sides of it, so this one would not be a chiral center. What about this molecule here, 3-methyl-4-propylheptane? Do I have any chiral centers? I got one, because this is also like an option, but this is a propyl group, and this is a propyl group, right? Those are the same size, so that cannot be a chiral center. So just the one. 3-ethyl-6-methyloctane. Again, just one, because this is an ethyl group, and this is an ethyl group, so that can't be one. And then lastly, do I have any in my last one? I do have one. This one would not be a chiral center because it's got 2 methyl groups on it, right? 2 identical groups. Cool. Now, we couldn't actually assign stereochemistry because we're not given dashes or wedges, right? We have no idea which direction that bond is pointing. So I couldn't actually ask you stereochemistry. I could just ask you how many chiral centers does that molecule have. All right, so then we complicated things by throwing in cyclic alkane nomenclature. Okay, and one of the ways that we complicated this is because there are some where we're going to have to include our cis and trans stereochemistry. All right, so let's go through these. Remember, when we're doing our cyclic alkanes, they have that cyclo prefix. This would be cyclopentane because it's a 5-carbon ring. If we have our ring with our substituents, the parent chain is always going to be the ring. So it doesn't matter that this substituent right here is actually longer than that parent chain. That's perfectly fine if we have a ring. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, so my parent chain here is that cyclohexane. My substituent here would be a heptyl group. All right, and when we put that together, we're just going to say heptyl cyclohexane without any locant on there. When there's only one substituent on the ring, we don't have to say it's on carbon 1 because it's always going to be on carbon 1, no matter where we put it. Right? So if there's one substituent, we shouldn't have any number out front. All right, so then for this one, again, my parent chain is that ring, 1, 2, 3, 4. This is a 4-carbon butyl group. This is a 2-carbon ethyl group. All right, now I have more than one substituent, so I'm going to have to number here. So I'm going to go 1, 2, 3. Or the other way, 1, 2, 3. In both cases, I have a 1 and a 3. So how do I break this tie? The alphabetical order. This was a situation that was pretty rare when you were dealing with normal alkanes, but you would see quite regularly with ringed alkanes, right? You get these ties a lot more frequently. So in this case, I'm going to pick my red numbering scheme. This would be 1 butyl, 3 ethyl cyclobutane. Okay. We get to this big one here. So again, we got our 1, 2, 3, 4, 5, 6, our cyclohexane. All right, but this one I wanted to do just to make sure we're careful that we actually do not have any sort of a tie break for this ring right here. There's one numbering scheme that will give us the lowest possible number, and that's if I start here at my propyl group. 1, 2, 4. There would be no other way of numbering it that would get you a smaller numbering scheme. So I don't have a tie here that I go to alphabetical for. Okay. When I put my name together, I'm still going to make sure, let me move, get a teeny bit of room here. Still going to make sure to put my substituents in alphabetical order here. So this is 1, 2, 3, 4, 5. So this is a pentyl group. This is a methyl group. And this is a propyl group. So methyl will come first. This will be 2-methyl. What's next? Pentyl? 4-pentyl. 1-propyl. Cyclohexane. Okay, so now are these compounds here? Now I have these dashed and wedged bonds. That's like even more information about the structure of this molecule, what we call the stereochemistry of this molecule. If I name this thing, without even paying attention to the stereochemistry at first, this is a 1, 2, 3, 4, 5, 6, 7-sided ring here. So this would be a cycloheptane. Okay, I have these 2 methyl groups located 3 carbons apart. So this would be 1, 3 dimethyl cycloheptane. Okay, but now because I'm seeing these dashed and wedged bonds, I have to include my stereochemistry here. I specifically was asking for the cis and the trans stereochemistry. Which one is this one that I'm looking at here? This is cis. And so remember, that goes out front of your name. You kind of build that stereochemistry into the name. All right, and then our last one here. Now we have a 1, 2, 3, 4, 5, 6, 7, 8-sided ring here. So that would be a cyclooctane. Okay. We have this 2-carbon group and this 3-carbon group. So an ethyl and a propyl. And again, we're in that situation where depending on where I start, I'm going to get a tie in my numbering scheme. All right, so again, we're going to go and break this tie with our alphabetical order. This would be 1 ethyl, 4 propyl, cyclooctane. And since I have those dashed and wedged bonds, I got to put my stereochemistry in there. This one would be trans. Cool. Just to go back, one of the other things that we were asking ourselves before was, do we have any stereocenters, any chiral carbons here? In my heptyl cyclohexane, is this a stereocenter? This is kind of hard to see for rings, right? Because they're connected. But nonetheless, if you start traveling this way, it looks the exact same as if you start traveling this way. So that would not be a chiral center, right? Same thing down here for this one as well, because they're exactly on opposite sides. So going this way, everything looks the same as going this way. So again, no chiral centers here. All of a sudden, if we get over here, now everything doesn't look the same, right? So this would actually have all 3 of these as chiral carbons. All right, so for rings, the symmetry of that ring, right? The fact that if I take a, I can sort of divide this symmetry, this plane of symmetry, and everything looks the same. That's how I can tell that this is not going to be a chiral carbon. What about here? Does this molecule have any chiral centers? Who thinks we got chiral centers? Raise your hand. Who thinks we don't have any chiral centers? Raise your hand. So this one does have 2 chiral centers, because look, if I go this way, I hit a methyl group. If I go this way, I don't. So those are not 2 identical groups there.
Even though they go the same path, they'll still be different.
Say it again?
They kind of have the same amount, but still be different.
Right, because look, this one has CH2, and then this carbon is different. Like as soon as I get 2 carbons away, these look different. All right, so this one indeed has 2 chiral centers. All right, but we actually have a special name for this type of compound right here, because even though it has these 2 chiral centers, it also has this plane of symmetry down the middle here. What was the name for those special kind of compounds? Meso compounds. This would be an example of a meso compound. A compound that does indeed have chiral centers, but is actually itself achiral. And you could convince yourself if you draw the mirror image of this structure, you would just be drawing the same thing kind of twisted around. All right, and then lastly, these would also be 2 chiral centers. Is this one a meso compound? No, because one half is an ethyl, the other half is a propyl, right? So there's not that plane of symmetry going down the middle of this molecule. If they were both, well, no, it still wouldn't work because they're on opposite sides. They're trans. All right, so then we really complicated things by adding in this concept of chirality. Every general or every first-year organic chemistry student, absolute favorite topic. All right, so for these ones, not only are we going to have to name them, but we're also going to add in their stereochemistry, specifically the RS stereochemistry. All right, so let's do this one. If I was going to name this without worrying about my stereochemistry, it would be 3-methyl hexane. All right, but now I have this chiral center right here, so I can specify the exact molecule I'm looking at by including that R or S. Okay, so what I got to do is I got to assign priority to each of my groups about that chiral center. If we call these A, B, and C, what's the highest priority group? B. And what's the next highest priority group? A, and then C. All right, so B, A, and C. And what's that fourth priority group? That hydrogen, that implied hydrogen. Whoops, I guess it's an H, not a 4. Cool. All right. So now my implied hydrogen is sticking into the page, so I can just connect 1 to 2, 2 to 3, 3 back to 1. And in this case, it's going in the counterclockwise direction, so this would be which isomer? S. And so how we do that is we put it in parentheses out front, S, 3-methylhexane. You could also say 3S, 3-methylhexane. Okay, and these are our normal rules where counterclockwise is S and clockwise is R because our hydrogen is pointed into the page. All right, if we do this one here, if we're going to name this, ignoring the stereochemistry, this would be 4-ethyl octane. Yep. All right, but I can specify the exact stereoisomer I'm looking at my chiral center here. Okay. The butyl is going to be 1, the propyl 2, the ethyl 3, and now my lowest priority group, this hydrogen, is pointed the wrong way, right? It's pointed out at us, but it's pointed exactly the wrong way, so we can just reverse our rules. If we go 1 to 2, 2 to 3, and 3 back to 1, we're going clockwise, but we're going to flip our rules. So now clockwise is the S stereoisomer, right? So when it was pointed into the page, it was counterclockwise, that was S. If it's pointed out of the page, our rules are flipped, and now clockwise is S. You could also take this molecule and redraw it, right? Flip it over and redraw it, but that's just a pretty easy thing to mess up. 4S, 4 ethyl octane would also work. Okay. So for this molecule, now I have 2 stereocenters. Or do I? No. All right, cool, right? So just because it's on a dash or a wedge doesn't mean it's a stereocenter. This one right here would not be because there are 2 methyl groups, okay? All that really means is that you can rotate about this single bond and you would get the opposite structure where it's on a wedge. You could easily convert between these two just by rotating that bond. All right, this one, however, is a stereocenter. Okay, there are 1, 2, 3 carbons on each side, but these are still not identical groups because of that branch point right there. Okay, so if we say A, B, and C, which one is my highest priority group? C, right? This branch point right here, because let's remember, what we're going to do is we're going to look at this carbon, these 2 carbons, and we have a tie because they're both carbons. So we're going to list everything they're bound to. Hydrogen, hydrogen, carbon. All right, we got another tie, so we're going to move down the line. Hydrogen, hydrogen, carbon, hydrogen, carbon, carbon, right? So that branch point right there is what makes that the higher priority group. Cool. All right, so this is 1, this is 2, this is 3. If we connect these, we are going clockwise. And what does clockwise mean for this particular structure? R. Excellent. So R, and then my name, 1, 2, 3, 4, 2, 4, dimethyl heptane. You could not, if it's not a ring, you can't give it cis or trans stereochemistry. And we could say R, or we could specify that it is that 4th carbon that is that stereocenter, so we could also say 4R. Either one of those would be perfectly acceptable. Okay, so now to be clear for these rings, this would, you could give it its cis-trans stereochemistry as well, but you could actually be even more specific by giving it its R and S stereochemistry. That's kind of like the next level of information that you can specify about a molecule. As I did here in our practice problems, I will on the exam, where I'm extra clear to say, hey, give me the cis-trans stereochemistry or give me the RS stereochemistry. So please pay attention to those instructions when you're doing this on the exam. Okay. I got a 7-membered ring here. All right, so we have these 2 stereocenters. Let's do this top one first. I'm actually going to make a copy of this and do it 2 places, so we can do it each one. All right, cool. So let's do this top one first, and then we'll do the bottom one second. Cool. All right, so again, we got to label these groups, A, B, and C. Which one is going to be my highest priority group? It's going to be C. Same thing as before. You hit that branch point very quickly, right? Actually, they're all equally tied at this first carbon here, right? Your list, H, H, C, H, H, C, H, H, C. So then you got to go down the line to the next one. This is now 3 H's. This is another HHC, and this one here is HCC, right? So again, you sort of break that. How do you know, if they all look the same, those branch points are going to increase the priority. So all that, again, to say that this is priority 1, this one's priority 2, and this one's priority 3. Okay, if I connect these, I am going in the clockwise direction. And what does clockwise mean for this particular bond? R, right? Because the hydrogen is into the page. So this one's R. Okay, so now let's focus on this next stereocenter right here. All right. Again, if we say A, B, and C, which one's the highest priority? B. What's the next highest priority? A. And C would be last here. So now I'm going to connect these. 1 to 2, 2 to 3, 3 back to 1. I'm going in the counterclockwise direction, but what does counterclockwise mean for this particular bond? Also R. All right, because now my hydrogen is on a wedge, so I got to reverse my rules. Okay, so both of these are R. So this would be, now we actually have to include the numbering in our name as well. This would be 1R, 3R, one 3-diethyl cycloheptane. Okay. And let me just real quick emphasize something. We said that these stereochemistry designations, these R and S, they're actually more information than cis or trans, right? Because this bond right here would be what? If I were to label this with my cis or trans stereochemistry, this one would be trans, okay? But if I take a very similar structure, but I flip those dashes and those wedges, that would also flip the stereochemistry of those two stereocenters. So these are both trans 1,3-dimethyl cycloheptane, but they are actually distinct molecules. One has one has both of its stereocenters in the R configuration. The other one has both of its stereocenters in the S configuration. Okay, so they're actually not identical superimposable molecules, which is why just saying trans is actually not quite as much information as specifying the stereochemistry of each of those stereocenters. Okay, we're going to find this cis-trans designation still super helpful. We'll still use it throughout the semester, but again, we can go even further with our information by specifying R and S. Okay, that was enough nomenclature. All right, so what are some other things that we did in this chapter that I could ask you about? All right, we got a bunch of stuff here. But if we're going to sort of just piggyback off of one of these same examples here, let's grab this molecule again. All right, I am going to pick this thing up, and I'm going to look at it down this bond right here, And you're going to draw me the Newman projection of what it looks like down that bond right there. All right, if you get your Newman projection, you will have drawn me a nice, stable, staggered conformation. I want you to twist it into an eclipsed conformation using that Newman projection as well. It's not bad. You just got to remind yourself that we learned how to do this, all right? I know, it was a while ago. And look, that's kind of the nice thing about nomenclature is once you get it down, we just redo it over and over and over again. So it's kind of not that bad once you crack the case, right? You got to remind yourself of all the little crap that we did sprinkled in throughout there as well, right? We talked a lot about these rotational conformations. Okay, we'll talk a little bit about boiling point. We compared molecules that way as well. There are some other little things that we did along the side. So my Newman projection, that first ethyl group is pointed up, so that's going to be right here. Okay, my methyl group, and to be clear, this intersection right here is that orange carbon. Okay, that ethyl group, or methyl group rather, is pointed out of the page, so that's going to go on the right-hand side here. All right, so what should I draw on the left? Just a hydrogen, okay? And now for this back carbon here, I put that into my Newman projection by drawing a circle. That represents my back carbon. So then I need to draw the bonds coming off of that back carbon. I don't have anything on my dashes or wedges, so those are two hydrogens. But then pointing straight down is that ethyl group, CH2, CH3, right? These remaining two carbons here.
So I never understood it like that. Top CH2, CH3, that's just the other atoms that are.
Yeah, so those, so if I color these here, those are here. And these here in the back half of my molecule, those are here. Yeah, so we're looking down one specific bond. Okay, so these are our nice, stable, staggered conformations where all of those bonds appear to be equally spaced. Okay, if I want to draw my eclipsed conformation, I'm going to keep everything on that front carbon the same. But then on my back carbon, I'm going to rotate those bonds so that now they are parallel, or at least as parallel as I can make them and still be able to draw in there, see what the heck's going on. All right, so these would be a eclipsed conformation versus a staggered conformation. All right, and if I wanted to draw the highest possible energy eclipsed conformation here, which one of those groups should I put parallel to my methyl or my ethyl group? That other big chunk, absolutely. Big groups do not like to be next to one another. So this would be my highest energy staggered or rather eclipsed conformation right here. When that ethyl group in the front that we colored in pink is eclipsed with that ethyl group in the back that we colored in green. That would be the highest energy. If you get, I just asked for any eclipse structure. If you gave me any eclipse structure, that was fine. But if I was asking for the highest energy one, that's when those two big groups are next to one another. Molecules don't like to be staggered. They super don't like to be staggered with two giant groups next to one another. Yeah, you don't have to memorize any tables. But yes, remember we did plot these by actually calculating what these values were. You did that graphing assignment. All right, y'all thought Newman projections was that, geez. All right, now let's remember what we did with cyclohexane. We spent a bunch of time talking about that chair conformation of cyclohexane. So you should be able to draw me the chair flip, and tell me which one is more stable. All right, so if I'm going to draw my chair, I got to start with those two parallel lines. And I'm going to put the bottom one, extend it out a little bit more. Connect them on one side with a triangle. And then I'm going to do the same thing, connect the other side with a triangle. Okay? I can tell that I have this drawn correctly if every other carbon is sitting at the peak of a triangle, and then the other ones are all sitting at a valley of a triangle. Okay? The ones at the peaks have their axial positions pointed straight up. All right, the ones at the valleys have their axial positions straight down. And everybody's got an equatorial position pointed out away from the ring. Okay, now I'm going to call this carbon 1 with my methyl group. Okay, and if I'm going to map that to my chair structure, I'm going to call this carbon 1 as well. All right, truthfully, you can start anywhere as long as you're consistent. So I'm going to put a methyl group on that first carbon. Since it's pointed up in my structure, it's going to go on the top bond on carbon 1. All right, so here's my first chair conformation. Okay, but this is in equilibrium with this flipped chair. In order to draw my flip, I gotta again draw those two parallel lines, but they're gonna be slanted the other direction. Right, so this is how I'm going to start off my flipped chair here. So to be clear, these two lines were my first two lines that I drew for my chair conformation. These are the first two lines that I draw for my flipped chair conformation. All right, drawing my triangles. Okay. And importantly, this was carbon 1 pointed up in my first chair. That means that it has to be pointed down in my flipped chair. So that is my carbon 1 in both of these conformations, right? That's the whole idea of a chair flip, is that your axial bonds turn into equatorial bonds and vice versa. So if I'm going to draw that methyl group on there, now it's not located on the axial bond anymore. It's located on the equatorial bond in my flip. And then which one of these is my more stable conformation? The one on the left or the one on the right? The one on the right. And why is that? Big groups want to be equatorial. Absolutely. That's what we want to remember. Big groups want to be equatorial. They just have more room. They're less sterically hindered in that position. Cool. All right. So again, there